As we move into Chapter 6, we are discussing our inverse circular functions. Now, you're going to need to recall some college algebra stuff here. We are finally getting to use those second function buttons above sine, cosine, and tangent, those inverse function buttons on our calculator, so you're going to need to have your calculator handy. Inverse functions. Now, from college algebra, just remember that we would take our function and invert it. We would do the switch and solve method. If I wanted an inverse function, I would switch and solve. So, for example, if I started out with f of x equals 3x plus 5, that's a linear function. It's just x. If I graph that, it's going to be a straight line. In fact, it will be a line that goes through the point 5 and has a slope of a positive 3. Well, if I want to invert this function, I'm going to replace f of x with y, and then I switch the x and y. So I make that switch, so I have x equals 3y plus 5, and now I need to solve for that new y. So I'm going to move that 5 over. I've got x minus 5 equals 3y, and then to finish solving for y, I divide both sides by 3, so that I have y is equal to x minus 5 over 3, and y, this is my inverse function, so I replace this y with my inverse notation, f inverse of x. And I could leave that like it is. I could write it in slope-intercept form. Doesn't really matter, but to go from my original function to my inverse function, I do that switch and solve method. Now, a function and its inverse are going to reflect across that line y equals x. So that if I have a function, let's say that I had these 3 points, and let's make this 0, 3, let's make this negative 1, 1, and let's make this negative 3, 1, negative 1, negative 3, negative, no, that's a negative 3, positive 1, sorry, negative 3, positive 1. If I'm going to invert these points, we can even connect those points if we want, but if I'm going to invert that, I'm going to reflect those points across the line y equals x, and I switch the domain and range. So my point 0, 3 becomes 3, 0. My point negative 1, 1 becomes 1, negative 1. And my point negative 3, 1 becomes 1, negative 3. I literally switch the domain and range. The x and the y value switch places. So that's how inverse functions work. Now, back to our notes for today. Recall that for a function f, every element x in the domain corresponds to one and only one element in the range if it's a function. Basically, that's our vertical line test. And here's a quadratic function. It passes my vertical line test. Vertical line test, right? Well, if I want to invert this and have the inverse be a function, it can't just be a function. It has to start out as a one-to-one function. You remember the one-to-one function. Well, the one-to-one function is also going to pass our horizontal line test. Now, our horizontal line test says that if point AB lies on the graph, then there's no other point on the graph that has A as the first coordinate. Other points may have B as the second coordinate. Now, this is if it is a function. However, since the definition of function allows those range elements to be repeated. So this is just my general definition of a function. The x values aren't going to repeat, but the y values can repeat. So like this is 2, 4, this point is negative 2, 4. Each x value has one y value, but my y values can be repeated. Now, if a function is defined so that each range element is used only once, then it is called a one-to-one function. And if it's a one-to-one function, it's also going to pass the horizontal line test. If it's a function, it passes the vertical line test. If it's a one-to-one function, it's going to also pass that horizontal line test. Well, my quadratic is a function, but it fails that horizontal line test. It's not one-to-one. So if I chose to invert this function, the inverse is not going to be a function. I can invert it, but it's not going to be a function. So let's take a look at that. Let's say we've got, there's my line of reflection. If I've got my parabola here, my quadratic function, and I invert it, it's going to reflect across this line. This piece goes here, and this piece goes here. This would be f of x. This would be f inverse of x, except this is not a function. Because when I invert it, now it fails that vertical line test. Fails the vertical line test. Well, could I fix that? Could I make that work so that when I invert my quadratic function, that it still passes the vertical line test? Well, I can, but to fix it, I would have to make it, I have to restrict the domain. So I have to say, okay, for my original function, I'm only going to look at half of my parabola. I'm going to restrict it to these positive x values. So instead of my full parabola, I'm only going to be interested in this half. X values greater than or equal to 0. F of x, such that my x values are just those positive x values. Well, now when I invert this, my inverse looks like this, and now that inverse is still a function. Because I restricted the original so that it was one-to-one, when I inverted it, it's still a function. Now, my y values ended up being restricted, greater than or equal to 0. After that one, it ends up being both of them. Okay, let's go back to our notes here and fill some of these in. Remember, you can always stop, pause, rewind, whatever you need to do. So to have a one-to-one function, it needs to pass both the vertical and the horizontal line test. Remember your cubic function. F of x equals x cubed. It's one-to-one. It passes my vertical and horizontal line test. It's a one-to-one function. So when I invert this, the inverse is also a function. F inverse is cube root of x. When I invert my cubic function, the inverse is also a function. Now, when I invert a function, what happens? The domain and the range switch places. For an inverse function, you exchange the domain and the range of the original function. So don't confuse, and it gives you a note. This -1 here is not a negative exponent. It doesn't represent 1 over f of x. It represents the inverse function of f. What does that mean for us for our trig functions? Well, for our trig functions, we start out with a domain as our angle and our range as our function value. So for f of x, we're plugging in an angle and we're getting out a function value. But for f inverse of x, we are plugging in a function value and getting out an angle. We switch our domain and range. Okay, summary of inverse function. You know all this already. This is just a good reminder. In a one-to-one function, each x value corresponds to only one y value, and each y value corresponds to only one x value for a one-to-one function. If a function f is one-to-one, then it has an inverse function. I can invert anything, but if I start out with a one-to-one function, the inverse will also be a function, f inverse. The domain of the function f is the range of its inverse, and the range of the function f becomes the domain of the inverse. That domain and range switch places. That is, if the point AB is on the graph of the original function, then the point BA is on the graph of the inverse function. Another neat thing about functions and their inverses are that they are reflections of each other across that line, y equals x. To find the function and its inverse, we use our switch and solve method. Switch and solve. And there's our steps for switch and solve. Okay, so we just did all of those things on that side work page and talked through them, and there you have them all in a nice, organized, neat table so that you can reference them when you need to. Okay, you're going to notice that we have graphs thrown in here. We're going to talk about the graphs. You will not have to graph these. So this gives you a visual idea of what we're doing with our inverse function, but I will not be asking you to graph inverse functions. So just keep that in mind. Now, sine function. I want you to think about our sine function graph. Our sine function graph is sine is a periodic function, right? That sine function starts at center, it goes peak, center, trough, back to center, and then this sine function continues on forever, right? Its domain is infinity. It just keeps going. This is not one-to-one. Absolutely not. Not one-to-one. But remember, just like our quadratic function, if we chose to restrict the domain, we can restrict it to make it a one-to-one function. And that's what we're going to do dealing with these periodic functions. We're going to restrict the domain of the original function to ensure that we are starting with a one-to-one function, to ensure that it is one-to-one. Now, you can restrict to any set of x values that gives you your full range of y values. It doesn't matter, but there's an established, kind of an agreement that this is what we generally do, the convention. And the convention is that when we're looking at sine inverse, we have restricted the domain of the original so it becomes the range of the inverse between negative pi half and positive pi half. At negative pi half, I have a trough. And at positive pi half, I have a peak. And between here and there, I include every function value for my original. So this is the restricted domain of the original function. It becomes the range of the inverse. Okay? When we restrict that, we end up with all the positive values, all the negative values. What has happened is we have essentially restricted it to two quadrants. So for sine inverse, we are restricting our function values from negative pi half to positive pi half, here to there, so that sine inverse is restricted to quadrants 4 and 1. And we do think of it as 4 and 1, negative pi half to positive pi half. This is the convention. This is the answers that I'm expecting you to give, okay? So we can think of y equals sine inverse, or another way to say that would be arc sine. Those are interchangeably used, doesn't matter which one you choose to use, as y is the angle in the interval from negative pi half to positive pi half whose sine is x. So that if I'm using my calculator and I get out I plug in a negative sine function, it's going to give me an angle between negative pi half and 0. If I plug in a positive sine function, it's going to get me an angle between 0 and pi half. The domain of the inverse is that range of that original function, so it's from negative 1 to 1. And the range of the inverse is the domain of the original function, which was negative infinity to positive infinity, but we agreed to restrict from negative pi half to positive pi half. So those are my restrictions for domain and range. That's a good thing to remember. So we restricted sine function negative to quadrants 4 and 1. Now this is going to be the restriction set for anything that is sine dominant, y dominant, so sine and its reciprocal cosecant. Also tangent we consider to be restricted to these two quadrants. Okay, let's find some inverse function values. Find the value y in each equation. Now this says arcsine, this says sine inverse. These mean the same thing. So when I'm solving and I have it in sine inverse or arcsine, my question is, what is the angle theta? What is theta? I'm looking for an angle. I'm giving you a sine function value, and I'm looking for an angle. Y equals arcsine of square root 3 over 2 means I want y, which is the angle whose sine function is square root 3 over 2. So I'm looking for an angle. Well, let's think about this. If you grab your unit circle, square root 3 over 2 is positive. Sine is positive in these two quadrants. But remember, I said that we are dealing with one-to-one functions. We have restricted it. So we restrict sine inverse to these two quadrants. If sine is positive, that means we're in quadrant 1. What is the angle in quadrant 1 with a sine function value of square root 3 over 2? Well, that's right here, pi third, or 60 degrees. So my answer here is pi third, or 60 degrees, depending on whether I'm wanting radians or degrees. Okay, so let me kind of divvy these up so that I don't end up running into space and running out of space. Okay, sine inverse of a negative 1/2. That means I'm given a function value, I'm looking for an angle. Sine inverse of negative 1/2. Sine function values are negative in quadrants 3 and 4, but sine inverse we restrict to these two quadrants, which means I'm in quadrant 4. The angles I'm considering are from negative pi half to 0. Well, if the sine function value is a negative 1/2, I'm right here, which is that 30-degree reference angle. Remember, I am going to return a negative angle value here. So that negative 1/2 means that my angle I'm interested in here is negative 30 degrees or a negative pi 6. That's the angle that has a sine function value of negative 1/2. Now, that is coterminal with a positive 330. I could go another rotation, I get another coterminal angle. I could keep rotating in a positive direction and get an infinite number of coterminal angles. But the angle you are going to return is going to be that angle that falls between negative pi half and 0. That's the standard agreed upon convention. All right, what if I have a sine inverse value that is square root 2? Well, square root 2 is more than 1, and that input for sine inverse has to be between negative 1 and 1. This is not an allowed sine function value. That does not exist. If I tried to use my calculator for that, whether I had it in degrees or radians, it wouldn't matter. If I do sine inverse of square root 2, it tells me there's a domain error because this value, that value square root 2, that value square root 2 lies outside the domain of my inverse function. All right, what about arcsine of positive 1/2? Sine inverse, sine arcsine is positive, restricted to quadrants 4 and 1, positive in quadrant 1. Where the sine function value is positive 1/2, we're right here. So that would be 30 degrees or pi/6. Where is sine inverse value -1? Well, that sine function value is a -1 at that quadrantal angle down here, which we want to say, oh look, 3 pi/2. But remember our convention. We're not going to refer to it as 3 pi/2. That is -pi/2 or -90 degrees. Where is my sine function value? A -2. Ah, sine doesn't go to -2. It falls between -1 and 1, so that is outside my domain. It does not exist. Gives me a domain error. Okay, now we're going to take a look at this graph for sine inverse, but remember you will not be asked to graph any of our inverse functions. We just look at it because it's a good idea to know what these things are going to look at. First, we have to be certain that the number given will be in the range of the particular inverse function being considered. For my sine inverse, the domain is the sine function value -1 to 1. The range is that agreed upon convention from -pi/2 to positive pi/2. We're used to seeing these two columns reversed. Remember, to get inverse function, you switch the domain and range. And that's what my function looks like when I take that restricted domain of the original and I flip it so that I reflect it across that line y = x. The inverse sine function is increasing and continuous along its domain from -1 to 1 inclusive. It is an odd function and it is centered on the origin. So sine of a -x is the opposite of sine inverse of x. Sine inverse of -x is the opposite value of sine inverse of x. Okay, just to fill that in so that you have it, you will be responsible for remembering domain and range for my inverse sine function. You do not have to worry about reproducing anything on this table. So let's talk about inverse cosine. Where my inverse sine function split on the y-axis is restricted to quadrants 4 and 1, inverse cosine, we need to think about, we need 2 quadrants for cosine, where we have a positive quadrant and a negative quadrant. Well, cosine is positive over here in quadrants 1 and 4, so we're not going to use those 2 quadrants. It's negative over here in quadrants 2 and 3, so we can't use both of those. But if we go from 0 to pi, cosine inverse is restricted to quadrants 1 and 2. That gets all of our positive cosine function values and our negative cosine function values. So our restriction for cosine is from 0 to pi. Now remember, we take the domain of our original. The domain of cosine would be all real numbers. We just restricted it to get our range of cosine inverse. The range of cosine function values is -1 to 1, just like sine. That becomes my domain of cosine inverse, -1 to 1. So let's skip these just for a second. Come down here to our chart. You're going to need to know this. Domain of cosine inverse is -1 to 1. Range is restricted 0 to pi. Cosine inverse is decreasing and continuous along its domain, -1 to 1. It has an x-intercept. You'll notice it is not balanced on the origin. It has an x-intercept at 1, 0. It has a y-intercept at 0, pi/2. It does not have any symmetry that we can predict. Doesn't have predictable symmetry. Okay, so now, getting your mind straight for inverse cosine function values. When I'm solving for y, I'm solving for the angle. I am looking for the angle theta or x. That's what I'm solving for. I'm giving you a function value. My cosine function value is 0. Where, at what angle is cosine 0? Well, cosine is 0 at pi half, which is the same thing as 90 degrees. Where is cosine function 1/2? Well, I'm restricting inverse cosine to quadrants 1 and 2. It's positive over here in quadrant 1. Cosine function value is a positive 1/2 right here, 60 degrees or pi/3 radians. Where is arc cosine 1? Well, that's my cosine function value. Again, restricting to cosine inverse arc cosine to quadrants 1 and 2. Cosine is a positive 1 at 0 degrees, which is the same thing as 0 radians. What about an inverse cosine function value of a negative square root 2 over 2? Well, cosine inverse, restricted to quadrants 1 and 2. It's negative over here. Cosine function value, negative square root 2 over 2 at 3 pi/4, which is the same thing as 135 degrees. You're starting to see again why the unit circle is so important. Being comfortable with the unit circle and able to reproduce it and visualize what angles are where and what their values are is going to save you so much work in trig and pre-cal and moving forward. Okay, let's look at this next page where we talk about inverse tangent. Now tangent, remember my tangent function value could be anything. So that tangent function value being anything, that output, the range of tangent, becomes my input or my domain of tangent inverse. It can be all real numbers. Because tangent has y in the numerator, we have a restriction for tangent that goes along for tangent inverse that goes along with our sine inverse restriction. So that my range of tangent inverse is restricted negative pi/2 to positive pi/2. The only difference here is that tangent is undefined at those pi/2. So it's not inclusive, it's just parentheses here. But my tangent inverse is restricted to quadrants 4 and 1, just like sine inverse, because tangent theta is y over x. So we go with the restrictions that we went with for sine inverse. That's my convention for tangent inverse. Not going to have to graph. You are going to have to know that the domain of your inverse tangent is negative infinity to positive infinity, and the range is negative pi/2 to positive pi/2, not inclusive. Now, once again, this is our convention. Some editors, some authors follow a different convention. It's possible that you will see things a little different somewhere out there online, but this is what our book is going to use as our decided restriction to make our tangent function 1-to-1, so that our inverse tangent is also a function. So we know our domain and range. This is what my function graph would look like. I've switched those columns from tangent x. The inverse tangent function is increasing and continuous on its domain, all real numbers. It goes through the origin, so it's odd. If I plug in a negative x, I get out the opposite of the value of tangent inverse of x. Those lines, negative pi/2, y equals negative pi/2, and y equals positive pi/2, give me horizontal asymptotes. I'm not going to ask you to graph inverse tangent. Good information to have so that you have it to look at, but you're not going to be asked to reproduce that. Now, here are our reciprocal functions for those three basic inverses. Cotangent is the reciprocal for tangent, but for cotangent now, my x is in the numerator. Cotangent theta is x over y. So I go back to the restrictions for cosine inverse. And when I'm dealing with cotangent inverse, I'm looking at quadrants 1 and 2 again. Notice that it's not or equal to. Secant is the reciprocal of cosine. So it also is restricted to quadrants. Secant inverse is restricted to quadrants 1 and 2 as well. But because secant is undefined at pi/2, it includes everything from 0 to pi except pi/2 because it's undefined there. And then cosecant is the reciprocal of sine, so cosecant inverse goes along with the restrictions for sine inverse, quadrants 4 and 1, but cosecant is undefined at 0 radians, 0 degrees. So it has to leave out that value. All right, let's take a look at some more of these. And you know what? We've already done a 30-minute video here, so I'm going to take a break. We've got 3 more pages of notes left. I'm going to take a break, and we are going to do this in 2 parts so that you hopefully will sit and think about this and let these concepts soak in before you move forward.